welcome. Thanks for being here so late. I guess, yeah, it's late. But I hope you're not asleep yet. So I'm going to talk about resilience-informed intrusion response in smart grids. As you introduced me already, so the aware reader who's not asleep sees that the email address does not really fit the company name anymore. So I'm not at AIT anymore for 1 month. That's why everything's a little bit mixed up here. But the work was done in cooperation with AIT, so that's why it's only fair to have everything in AIT style and acknowledge that. Okay, so what am I going to talk about today? A short outline. Why do we need intrusion response for smart grids? What use case? So smart grid is a massive topic for those who looked into it in some depth. So what are we focusing the research on that I'm going to present? And then the two sort of research-focused parts of the talk. One about what do we mean when we talk about resilience, and why is that important? And then how can we use it for intrusion response, and what are the challenges there before we wrap up. So why do we need this? I mean, newspaper articles are full over the last years. Steel plants, attacks on artillery units by the Ukraine military, coordinated hack attacks on the Ukraine power networks, attacks on the US power grid. So there are enough examples that motivate that security in this domain is not sufficient, to say the least. And there are a lot of discussions why not more has happened until now. Yeah, there are various theories, but I think the clock is ticking in doing something to protect the domain. So when we talk about the smart grid, what makes a grid smart? So in general, we talk about power transmission, and traditionally, everything was very nice and tidy. We had an isolated network. We had some control center that would communicate with the generation and with the transmission system or the distribution system, depending on high or low voltage parts. And the power flow is very linear. So there is a bulk generation, like an atomic power plant, water power plant, generates massive amount of energy, and then it's transmitted to all the households over various power lines, and there it's used. Now, at some point, people thought maybe that's not the best way. So the control center envisioned a model where they could do remote access to all the systems, so they don't need to send the engineers out anymore. And actually, power prices that are static are not that useful anymore. There are climate goals to achieve, so everything would be much nicer if I can do automated billing by the second, changing dynamics in the prices, and so on. So on the generation side, we got renewable energy sources. The transmission and the distribution systems are under challenge due to those renewable energy sources, so the whole structure of the transmission system changes. And on the consumer side, basically we roll out smart meters and then you get load management, so your washing machine runs whenever the price is low, and you have your own distributed energy source, so your PV on the rooftop actually feeds energy back into the grid. But if you remember this linear transmission, it's basically broken up because now you're feeding energy from the wrong side, so everything gets much more complex. And without going into too much detail, something at the end, it could look something like this, which is much more complicated. You see that there's distributed energy resources on the other side. There are a lot of different communication networks, and all of this needs to be managed somehow. The problem is, with this increasing complexity, a lot of additional attack vectors are increased into the domain that are usually prevented by, we have an air gap and everything's fine, we can do whatever we want. And we just do physical security on our substations, for example. So, yeah, when you look at this, you cannot talk in a research project about securing all of this at once. So you need to focus on a specific use case that's representative for whatever a future smart grid would look like. So the thing that we chose is synchronous islanding, and what it is, I'll explain it now. So basically, one idea in the smart grid is the concept of microgrids. So rather than having one massive distribution grid, you break it up and you say this part of the town is a microgrid. It generates its own energy and it consumes the same energy at the same time. Everything in close local proximity to each other. And in case that there is sort of a need for more energy, you buy it from another microgrid that's next to you or from the main grid that's somewhere else. That's the theory, but the benefit of that would be if the main grid has a problem, I can disconnect, I can do my own thing, I don't have an outage in my domain of my microgrid, and whenever the main grid is back on, I reconnect and I can do energy trading and make money out of the energy I don't need at the moment and so on. So it's sort of a marketing system, a distributed system in energy. So if you think about this, in this setup, you could have a very simple microgrid like this. There is a controller, there is some DC machines or generator, there are some loads, and there's a circuit breaker that connects it to the main grid. So a circuit breaker is basically just a switch. You close it, it's connected, you open it, it's disconnected. And then the microgrid works on its own. So it's connected to the host grid, whatever that means in this scenario then. It's just a much more, in general, much more stable grid where you can get additional energy if you need it or sell energy to if you don't need it. And then you have some sort of corporate network communication that's needed because there is a critical point in time when you reconnect a microgrid to a main grid. If you think about DC energy, no, AC energy, sorry, and you have this sine curve. And in order to reconnect two systems, the sine curves have to be aligned. So that gives you three parameters. One is the voltage in the two systems that you want to reconnect. The second one is the frequency of the curve. And the third one is the shift in the curve in time to some specific reference. And all of those three you need to have at the same point in time, have to be overlapped. Otherwise, that is a problem for the physical equipment. Why? Because if they would be 180 degrees shifted at the moment you close, physics force the two systems to be aligned at that point in time. That means if you have a massive rotating mass that's generating your energy, for example, water plant somewhere in the Danube, then at the point where you reclose it, this massive machine has to stop because it has to shift 180 degrees at that point in time. And this physical load would put stress on the equipment and something would break, blow up. In general, something bad would happen. So we have to guarantee that this is not the case. And how do we do that? We have these devices called PMUs. They basically send these three types of information multiple times per second. And they are synchronized in time. So you can compare the two information points from within your microgrid and in the main grid. And then by combining them, you can sort of adjust your microgrid. So before you reconnect, you look, am I similar? No, I need to speed up a little bit, I need to slow down a little bit, I need to adjust that the two curves are aligned. And once they are, I can safely reclose and everything's fine. Now, that obviously sounds like perfect opportunities for attackers, right? The moment that I manipulate those things, everything falls to pieces. So what can we think of as attacker models? So if we remember at the end we want to do intrusion response, so first we need to consider what do we want to respond to, what are the types of attacks that our system can actually mitigate. We're not doing machine learning, we cannot automatically detect any type of attack and mitigate it. We need to properly define in advance what are the types of attacks that we are considering. So things that we want to consider are normal operation, we need to detect it because otherwise we do stuff that's not needed. Then we have the case that the devices are faulty, so we get strange measurements. We can have quality of service issues, either erroneous because some network device fails or because there's a DOS attack or something like that, so the packets are not coming through in time. And then we can also attack the measurements. So we focus on frequency and phase angle, which is the shift of the curve. So if you think of those, they're just two numbers that are coming through 10 times, 6 times per second, whatever, depending on the standard that you use. So one thing is we can just take the phase angle measurement and replace it with something else. Right? Usually as an attacker what we want to do is we want to replace it with something that's 180 degrees shifted. That's the worst case scenario. Perfect. So we replace it, the controller thinks everything's good, switches reclosed, everything blows up. Perfect idea. So if you measure that, you get this curve. So you see at this point in time, at time 40, we inject the shift in the phase angle, and the blue curve is the thing that we would like to have. The red curve is what we actually get. Perfect. It's a perfect shift of the curve. This sawtooth curve is just the way it looks. It could also be flatlined. It depends on what you use as a reference point. So, and we also see at the time that we inject this, we get sort of a oscillation in the frequency domain, which is just above. It's the same thing at the same time, just a different value. So there's sort of a challenge to the system, and the controller adapts and says, okay, we have a new phase angle, so we have to speed up, adjust, everything's fine again. The frequency stays the same, so we are again getting back to the nominal frequency. Looks perfect, very bad. Second thing, we can manipulate the frequency. So instead of changing the second value, we change the first value. And there we see that's not so easy. Why? Because the two values are correlated. If you increase the frequency, then the phase angle that you get won't match the curve that you would expect. So that it's sort of oscillating, but you say it's quicker than it is, so the controller doesn't know what to do. So there's one case, if the change is small enough, then you get the, that I don't say anything wrong, then you get the red curve. If you change the frequency small enough, then it's compensated by a shift in phase angle. So it looks fine, but if you change it too high, then the controller cannot cope. The error in phase angle increases, then it tries to compensate the error in phase angle, introduces an additional error in frequency. Once the frequency error gets high enough, it tries to compensate the frequency error, but then the phase angle error is too high. So it starts to oscillate and you don't get a stable thing anymore. So as an attacker, you actually cannot, that way you cannot intelligently manipulate the frequency as you want, because that's easy to detect, right? If my controller starts spinning around like crazy, something is wrong. But what you can do is you can change both at the same time. You'll just take a different voltage reference, a system that's not the system that you actually want to synchronize to, but something else. It's running a little bit faster, and everything works perfect. You get two values that are not the ones that are really in the system that you are looking at, but the two values add up at all times, so the controller just finds a different stable frequency up there, and the phase angle is just quicker. But as a controller, you can never be sure that you are able to synchronize. There are points in time where it's safe to synchronize, there are points in time where it's not safe. So as a controller, you have to assume in this type of attack that it's always the worst case, because you don't know better. So that's actually the worst case scenario from a mitigation point of view, because we don't have any clue what's going on. We cannot detect it from a power engineering point of view, because it's a valid reference, but we also cannot trust our data anymore. So we need to do something about that. So we are talking about intrusion response. Why are we talking about intrusion response? And why are we talking about automated intrusion response? It's sort of this holy grail of IT security. We do everything automated. Everyone here is not needed anymore. Just the system running. If something's going wrong, you mitigate it, done, right? Obviously, it's not that easy. And also, it's only working, it's working specifically well in smart grid scenarios, because you can do stuff to the grid without the need to mitigate the attack itself. And we will see how that works. So how is the setup working, and what am I going to talk about today? So I'm not talking about everything, but we are saying we have a system. We already talked about the system, right? And the system generates data. It generates data on the OT side, so on the operational technology side in the grid. It also generates data on the IT side. So you get all the stuff that you know, you get all the senders, host-based IDS, network IDS. You have physical sensors that's traditionally not really useful in classical IT systems, but it is in this type of scenario. You have anomaly detection maybe, something that we heard in the previous slot. You could do anomaly detection on your data in your OT network or in your IT network. You have antivirus scanners. So all of this data is available. We are not talking about where to get this from. There is enough research out there at the moment. So what we need to do is we need to combine that information that's from those sensors. We need to combine it in a sense that we get information about causality. So traditionally what you do is traditionally IT security systems or CM solutions, they correlate. So you say this and this is always happening at the same time. Perfect, there's a correlation. What they are not as good in doing is talking about causality. So because this happens, this other thing happens. That's a much, much more difficult problem to solve. So that's not something that we are able to solve, or at the moment, we were not, solve as a sort of a blueprint that works for everything, but we can solve it to a certain degree for the use case at hand. I won't also talk about this, because that would blow up the length of the talk, but we have a paper on that, so if you're interested in how we achieve this, I refer you to that. And then the things that we talk about today in more detail are the two aspects that we need for automated response. So first, we need some notion of cost, because we deploy a mitigation action, and if this mitigation action would be cost neutral to our system, it would be in place all the time, right? So if I can say you can be more secure and it costs you nothing, you would just do it all the time. So that's not that's not something that you do dynamically. So all these mitigation actions that we do will cost us something. The question is it cheaper than the attack? Because then we want to deploy it. But if it's more costly, then, for example, in normal operation, we don't want to deploy these things because normal operation is good for us, and if we deploy it, it costs us money, so we don't want to do it, or it costs us something else. This something else, in our case, is resilience. We talk about how we measure resilience. The second thing is, once we have this model of cost, in our case, model of resilience, then we need some knowledge on how we can decide what's the optimal choice for our use case of our situation in the system at the moment, right? Should we deploy action A? Should we deploy action B? Should we deploy them both? Should we deactivate one that's already active? Because this is all the time running. So it's a continuous process that's also highlighted by this feedback loop. So you always get new information from the sensors, and you always have to adapt what you're currently doing in your system. So those are the things that we talk about. Now that's so far for the introduction to everything. Now it gets a little bit more technical. Yeah, just bear with me. I hope it's not too much. So what's resilience? There are various definitions on resilience out there, very ambiguous. It's sort of everything and nothing, but if we combine them, we can get a sort of a clear understanding. So one example is it maintains state awareness. So it's a system, a resilient system is a system that maintains state awareness and an acceptable level of normal operation, although there are unexpected and malicious disturbances to the system, right? So we have disturbances and we are still working as expected. Then we can mitigate most undesirable incidents, so that would be the preventive part of security. Then if there is something that comes through, it should be minimized in impact, and then we can recover. So once this thing happened, we can come back to normal operation. More specific to smart grids, there is a continuous electricity flow, and we can respond in real time. So different research papers, different views on resilience. It's very difficult to get a clear handle, but the general concept is very clear. So how do we see this general concept? So in our research, resilience is defined by 3 potentials. Those are the 3 things here. So one is absorbing potential. So if an attack comes in, I want to absorb it. That's the perfect case is I absorb all of them, then nothing goes through. That's not going to happen, we know that. So I need something else. I need 2 more things to be resilient. One is I need survivability. So if an attack goes through, my system should not collapse, because once it's collapsed, from a resilience point of view, the system is not working anymore, and I need external influence to the system to get it back up. If an attack is able to do that, then for a critical infrastructure like a smart grid, that's really bad. So we need some sort of notion of measuring that the system stays alive at all times, although there is an attack. And then the last thing is recoverability. So there is something going through, it degrades our system performance. The system stays alive, but not as we want it. So our system has to be able to get back to normal operation. So these 3 things define how we see resilience, these 3 aspects. And then we can measure resilience sort of as the system performance, that's this blue curve, over the time, which is on the x-axis, and there is some sort of challenge, either malicious or erroneous, so a server fails, fuse blows, a tree hits a mast. All of these things can happen, they're random, or there are cyber attacks which are malicious, and all of those feed into the system resilience. So how can we measure it? That's where it gets a little bit tricky, but I will try to skip over those, as I don't have that much time anyway. So, so how can we measure it? We can measure it as a ratio between the blue curve, which is how far my performance degrades, and the green block, which is basically my worst case scenario. So in my worst case scenario, my system fails and never comes back up, right? So that's the worst case. So the smaller the blue curve gets in relation to this green block, the better my resilience. In the optimal case, it never degrades below this certain threshold and everything's fine. There will be some oscillation in performance, but not too much, so we're good. The moment it degrades too far, we have to measure it, but that's sort of easy, just looks mathematically a little bit complex. But then the problem is, what is this performance curve? It's not one thing. You cannot say performance is I distribute that much load to a consumer. If you ask an IT engineer or someone in your IT department, it would define performance of the system as something different than you ask the electrical engineer, than when you ask the consumer, or when you ask your finance department. So it's sort of not that easy as saying there's one curve and we can measure it and that's perfect. So we need some understanding of how this works together, and that's where we have different performance indicators, and they are all related to each other. So we measure those as differential equations, and then it's a big system of differential equations, and all of these performance understandings affect each other. So there are a lot of cross-references in there. I will skip over a lot of slides here, so all of these parameters have an impact on how the resilience is measured. So I guess if you are more interested in what each of these mean, then look at the slides afterwards, I guess. I'm probably boring someone here with that. So the key takeaway here is that it's not one performance, it's a lot of performance indicators that affect each other. For example, quality of service can affect, or a denial of service attack affects the quality of service of my network, which affects the operational performance of the controller, which affects how well my system works. So in the use case that we are looking at, we defined what we want to look at, and that's how it looks. So we consider from the physical domain, we consider load changes. From the cyber domain, we consider manipulation attacks and denial of service attacks, and then there are intermediate performance indicators and some final performance indicators. So it looks like this, like a vector of performances, and we can compute that, and we can pick one and say that's the performance that we want to measure, depending on our use case. So in our case, we look at the phase error down here. It then looks something like this, so you can estimate how your resilience will be in certain situations. So you can input into a model of these differential equations, you put in what your manipulation is on the frequency domain, what your denial of service strength is, and what the load change is, and then you get some results in the frequency domain and some results in the phase angle domain. And there are measurements, so that the nice oscillation curves are measurements from our system, and the red curves are the estimations that are done by the model of differential equations. So we estimate it. We don't really model the complete system in its full complexity. That would not be feasible. This is hard enough. Okay, and then there is a lot of stuff about the decision making. I will skip this slide because it's more the formal definition, but we'll talk about it here. I'm sorry that there should be just a table here. Just ignore the stuff at the bottom at the moment. It's a little bit of a complexity with the PDF file here. So what are we looking at? We are interested in a system state. So what's the state of our system? And we are interested in what are the mitigation actions that we can take, and what costs each mitigation action in each situation of our system. So the columns are the system states, C1 to C18 for our system, and they are defined by 3 variables. So the quality of service in our system, the status of the PMU in our system, and the state of the network. Is there manipulation or is there no manipulation? All of these things can happen at the same time as well. So in the sort of C18 is the communication is lost, the PMU is manipulated, and the traffic is manipulated as well. So that's like the worst case that we can get. In the first state, it's all of those are 0. That means everything seems to be normal. So we get all of these states, and we have 3 mitigation actions. Those are the rows. And now we can populate this table with the scores from the resilience metric. So we have the prediction. We can put in an estimate of how bad this attack is going to be, and then we can populate this whole matrix, and then we can compute which the optimal decision is. Now we need to combine 2 things. We have this table, but we also need some information about what state we are in. That's where this part comes in that I didn't talk about in too much detail. This combination of sensor evidence to get this system state. So what we are using is a mathematical model called evidential networks. But at the end, it's a distribution. It's a normal probability distribution, but it includes uncertainty. So there is an example here. So a possible system state that evidential network would provide is it's 70% sure that it's either state 1, 2, or 3, and 30% sure that it's exactly state 1. So the first part of the distribution, of this probability distribution, tells us there is a certain there's an uncertainty in there. It doesn't split the 70% up on each state, but it says I'm not sure where I am in this area of states. And that's difficult, but also gives us the benefit that it's easier to design these models. So, and the system is never going to be completely sure what we are looking at. So it has this complexity of saying, I don't know exactly, figure out what you want to do with this information, but I can give you a direction. And now the question is, how can we compute this? And what we do is we can, the key takeaway from this slide is basically there is a value beta, somewhere in here, or it's not in here, it's on the next slide, where I can decide how my decision-making unit should resolve this uncertainty. So a risk-taking decision maker would say, I'll take the best option in that case and I prioritize this. And the risk-averse would say, I want to prevent the worst case. So I'll take the one that's the cheapest if nothing is going on, and the risk-taking one is I take the best one if everything's going to the bins. So you can sort of configure your system and it decides how it should resolve the complexity by itself. So yeah, there is this beta value that I mentioned. So there's much more complexity to this. So we get not one table, but we get multiple, because when we activate an action, then all the scores have to be flipped, because then I have to decide, should I deactivate it again, right? So if I say we should do something differently now, then in the next step, my system state changes, the attack is gone, then I should reverse this action because it costs me something in normal operation. So I guess I'll jump over the results here. So you can see how the beta value affects the decision. So there are the different scenarios, what type of attack is executed. Here are the types of mitigation actions that we used. And you can see that depending on the beta value, it chooses different mitigation actions automatically because it's more risk-taking or more risk-averse. And then you can also see how the different mitigation actions affect our system operation. So in this case, there are certain cyber attacks happening, and depending on the risk level that you, the risk aversity of that you put into your model, you get a different mitigation action. And you see that in this case, A2 would be optimal, right? Because the frequency is the lowest deviation from all, and the phase angle is sort of stable. It's not optimal, but it's better than the cyber attack case. And it's something that we can manage and we have control over. In another case, the A2 is not that good. It's just oscillating massively, but other decision makings are better. So the system is able to decide based on the attack model that it's detected which mitigation actions should be taken. All right. There are some conclusions, so I think I have to stop. Yeah, so there are new challenges, and automated intrusion response is not at that point where it's a silver bullet, but it's useful in cases where you have a high time criticality, where a human intervention is not feasible. So in this case, where you get measurements every multiple times per second, this would not be feasible. All right. Thanks.